Today, we are going to discuss how to design recommendation systems using graphical models and neural networks. The primary algorithmic approach for recommendation or personalization that we have discussed so far has been based on the view of matrix completion. We view user preference data as a matrix, and the goal of the recommendation algorithm is to complete the matrix by filling missing entries in this matrix. The view of matrix completion provides us a way to fill missing preference data. This view, however, has few limitations. First, the matrix completion view assumes that the relationship between preferences of users is somewhat simplistic. It could be explained by a simple relationship that is behind collaborative filtering or matrix factorization algorithm. In reality, this relationship could be quite complicated. Second, the matrix completion view assumes that the user preferences are static. In reality, user preferences evolve over time. For example, movies that may seem excellent choice now may not remain excellent choice a decade later. Today, we shall discuss how to address these two challenges. We will discuss an approach to address them using formalism of what is known as graphical models. Okay, so what are graphical models? Well, in a nutshell, graphical models provide succinct representation that can capture a generic dependency relationship between various objects of interest. This representation is of particular interest in statistics and machine learning because it is amenable to scalable computation. Precisely, what we shall discuss is how to use graphical model to address these two challenges. First, probabilistic graphical models will help us capture intricate relationship between user preferences. Second, graphical model with Markovian structure can capture the temporal aspects of user preferences in recommendation system. Let us start by discussing how probabilistic graphical models can help capture intricate relationship between user preferences. For the purpose of explanation, we shall rely on our favorite Netflix example. We have users and movies. We shall assume that each user either likes a movie or dislikes a movie. For example, suppose we have 4 movies: Casablanca, Iron Man, Godfather, and Batman. Then we have 4 nodes in the graph. The edges between these nodes should capture relationship between the movie preferences across all users. Intuitively, an edge between Casablanca and Godfather might suggest that there is some form of relationship between preferences of users for Casablanca and Godfather. For each user, each node is assigned value +1 or -1, depending on whether that particular user likes that movie or does not like that movie. As a collection, all users are defining a distribution over +1 and -1 value assigned to all nodes. It is this distribution that the graphical model captures using appropriate edge structure and associated parameters. And it is this distribution that is truly capturing the relationship between preferences of all users. So now let us discuss what are the parameters associated with the graph. To describe them, we shall consider a specific parameterization for such a graphical model, also known as pairwise graphical model. In this parameterization, there is a distinct parameter associated with each node and edge of the graph. In the 4-node graph example, let us say θ1 be the parameter associated with node 1, and so on. There are a total of 6 pairs of edges, and hence, in principle, there are 6 edge parameters associated with them. These parameters describe a distribution of the 4 nodes taking +1 or -1 values as follows. So let us say sigma 1 denotes the value associated with node 1. It could be +1 or -1, and so on. Then the probability of the 4 variables having this particular assignment is proportional to the following formula. Let me parse the formula slowly. Probability is proportional to exponential of summation of 2 terms. The first term is the summation of 4 elements, each corresponding to one of the 4 nodes. The second term is the summation of 6 elements, each corresponding to each of the edges. The graphical model thus described encodes the relationship between user preferences over movies through these node and edge parameters. For example, if user population is such that they all like all the movies. The parameterization, where edge parameters are equal to 0 and node parameters equal to infinity, describes the corresponding graphical model. That is, the graph has no edges. In practice, the parameters need to be learned from the observations. The model captures relationship across all movies. Therefore, at first glance, it may appear that we will need to observe users' preferences over all movies to learn all these parameters. Can we learn parameters of the graphical model from sparse user preferences? The answer is somewhat surprisingly yes. It suffices to observe very little data as long as across all users we have observed preferences between all pairs of movies. We should be able to estimate the pairwise moments of all nodes. It means that we should be able to estimate the following: the fraction of users that like both movies, that like one movie but not the other one, and the fraction of users that dislike both movies.